This question is about the equilibrium mixture formed when A and B react. A solution containing 0.60 moles of A is added to a solution containing 0.60 moles of B. The amount of C formed at equilibrium is 0.28 moles. Deduce the amounts of A and B in this mixture at equilibrium. So we're having to work out how many moles are left at equilibrium. I like to do this using a method called RICE or ICE, depending on how you might have come across it. I like to put the R in for the ratio. So the ratio in this equation is 1 to 2 to 1. And the initial amounts, 0.6 of A, so the I stands for initial, 0.6 of B, and there'll be no C at the beginning. And then at equilibrium, there is 0.28 moles of C. So we can see that C has gone up by 0.28. Our R and RC line need to be in the same proportions. And so 1 to 2 to 1, if C is a 1, then A is a 1, so 0.28, but reactants go down. And then B goes down by 0.28 times 2, so minus 0.56. Apply those changes to the initial amounts. You get 0.32 of A and 0.04 of B. And we can write those on our answer line, 0.32 of A, 0.04 of B. Then it says, give an expression for the equilibrium constant Kc, remembering that the C stands for concentration and that we're going to do products over reactants. So we've got 1C, so the concentration of C, over 1A, so concentration, square brackets for concentration, and then B twice. So because we're becoming multiplied, 2B's becomes B squared. Make sure you've got squared brackets. The temperature of the equilibrium mixture is decreased. So if we just go back, we need to have a look at that equation. It was delta H is minus 32. So this was our equation, A plus 2B in equilibrium with C. Delta H is minus 32. The forward reaction is exothermic, negative. Okay, so when temperature is decreased, equilibrium will shift in the direction that warms it back up to oppose the change. So it's going to shift in the exothermic direction, which is forwards, we've just written. And it does that according to Le Chatelier's principle to oppose the decrease in temperature. And so if we're shifting to the right, and this is an effect of temperature, then we're going to have more top line and less bottom line. And this is, temperature is the only thing that could affect a Kc. But because we're shifting to the right, the value of Kc will increase. We're getting more products, less reactants. In another mixture, A is 0.48 and C is 0.62 concentration. It says, for this reaction, the equilibrium constant Kc is 7.8. Calculate B. So just to remind ourselves that our equilibrium expression that we wrote was C over A B squared, and we're having to calculate B. So if we rearrange, first of all for B squared, we'll get C, concentration of C over concentration of A times Kc. So if we want the concentration of B, it's going to be the square root of the concentration of C divided by the concentration of A times by the Kc. So if we type in the values, we're going to do the square root of C, 0.62, over A, 0.48, times Kc, 7.8. So if we put that on your calculator, remember you can use your calculator to do that. Press the square root button, press the fraction button. Type 0.62 on the top line. type 0.48 times 7.8 onto the bottom line and execute that calculation. 0. And we need to give it to the appropriate significant figures. We've got 2, 2, 2. So we want to give our answer to 2 significant figures. The calculator's saying 0.406937697, but to 2 significant figures, we're going to cut it off here, and the 6 is going to round us up to 0.41.